Hi there, Physics 152. This week's practicals are all about oscillations and simple harmonic motion, and maybe not so simple harmonic motion. But there are two main experiments. First is a mass hanging on a spring, so it's a vertical spring. Here's the mass, here's the spring, and then to measure it, what we do is we use the motion sensor. So the motion sensor sends out a little click of ultrasound, which allows it to measure the distance to any nearby object by measuring the echo time, the time for the pulse to go out, reflect off a nearby object and come back. So we aim it upwards. Now, I've got my thingy set into person mode as opposed to cart mode, which I find works a little better. It's a wider beam. And I set it up underneath. And now to get this working on a computer, you have to go to LabVIEW shortcuts and then click on motion sensor. I'm going to set it up right underneath. This might take a few trials to get this actually working. But basically, then you click on Start Detector, and then you click on, well, actually, let it go. You can't have it go closer than 15 centimeters to the detector, because then the time for the echo gets less than the minimum amount of time it can measure. So you have to make sure that the mass is far enough up, and then when you're ready, one of your friends can let it go, I guess, or you can let it go. And once you want it to bounce straight up and down, just a little hard. And then you click collect data. That's not so good. I think I'm going to go on set up calibrate, change it to 60 samples per second, because 10 is not good enough. Let's try that again. Every time I click on collect data, it erases the data and starts again. So now we got a nice sort of sine wave. And I can turn that off. I can click on Analyze tab, and that gives me distance, velocity, and acceleration. I think it's all in centimeters per second, and centimeters per second squared. So you can analyze that. The other big trick here that you're going to have to do is to try to figure out what the spring constant of this spring is. The way you can do that is you can find the equilibrium position of a mass hanging on the spring, and then you know the force acting on the spring, which is going to be equal to the force of gravity acting on the mass, I think, because there's a upward force of the spring, which is equal to the downward force of gravity on this mass. But then you have to measure the equilibrium distance, and I think the only way to really do this is to get two different masses and measure the difference in equilibrium positions, and then measure and then subtract the difference of those two forces and divide those, and you'll get the spring constant. So I'll let you think about that a little bit. So the next experiment is called Activity 9, I think, and it is about pendulum motion. So you've got a what's called a rotary motion sensor, which is next. You can connect this to the DAC device. I think what you do, you put it in digital channel, you hook up the yellow to yellow and the black to black, and then attached to it is a rigid rod, and at the bottom of the rod you've got a mass, and your first task will be to measure the distance L from your text. It's basically the distance between the center of the mass, the biggest mass, and we're going to, I guess, neglect the mass of this rod, maybe, and then the pivot. The pivot point, I can see, around 30, 34, 35 centimeters, something like that. So then what you do, go to the computer here, again, click on LabVIEW shortcuts, and what you get, you see RMS. So you open up RMS, that's rotary motion sensor, you click acquire data, and basically it is measuring the angle in degrees as a function of time. It seems to be positive when you go clockwise and negative when you go counterclockwise. So that's good. Now, one thing I will just tell you is I just checked the nice fact here that when I go from like a full circle around counterclockwise like that, then it registers as 360 degrees. That's good. I find that this rotary sensor sometimes makes a mistake by a factor of 2 or 4. Don't know why, but I've swung it right around in the circle one time and got 90. And that's not good. But if you unplug it and then plug it back in again, it tends to fix it. Again, don't really ask me why. It's something to do with the counter in there. So, and I guess the software. So sometimes you might want to try that. I think your first task is just to make sure that a full rotation is 360 degrees. After that, yeah, you want to do your experiment. I would, whenever you click on acquire data or clear data and acquire data, it starts at 0. So I would start your motion and then let it oscillate a little bit. And what you want is sort of these data right here. So at the beginning, I was actually just setting it up, but then it gets into this nice oscillating motion. You can explore different angles if you want, and in fact, it's possible to even start this thing way above 90 degrees and let this thing oscillate. And that is going to turn out to not actually be simple harmonic motion. Okay, the next activity is activity 10, which is a Python activity to try to simulate the data you got for the actual pendulum. So you have to run this code, which is in Appendix 1. So you can download this pendulum.py. You want to do save file. You don't want to open it up with CodeWriter. That sticks it into your download file or download folder. So if you show it there, you can probably drag it over onto the desktop, and then you can edit it and open it up and use it. And the way you want to use it is with Spider. So you double click on Spider, and now we play the waiting game. It's a while for Spider to come up, but you must be patient. Oh, look at that. Okay, good. So now you've got Spider. You want to open that file that I placed on the desktop. I can click on desktop, and there it is. Should be able to see that it's a 2022 version, and then you can press the play button to execute in current console, and it gives that output. The other thing that it does, it creates a CSV file called pendulum output, which you can open up with Excel if you double click on that, and that gives you a plot of time and angle of this simulation. So you can highlight that, click on insert like a scatter plot or something, chart, and do XY scatter, and then you can get a very nice sort of graph thing. You can do axis titles, something like primary horizontal. You could do time in seconds, say pod 9 or pod 8 plot. The other thing you can do is, of course, send this to the printer. File print. Which should send it to the printer at the front of the room. And that way you can actually staple it into your lab notebook and include it as part of your analysis. So that's your intro to all the activities for this week. I hope that was helpful, and I'll be seeing you next week. Take care. Bye-bye.